Bonjour élèves, aujourd'hui English. Hi nerds, we're gonna work on quadratics today. You can tell it's parent-teacher conferences, and I've been trying to speak as many languages as possible. Also, I like wearing a suit. We're looking at quadratics, and quadratics in transformations, which is like how to take a quadratic and like switch it around. So it's a nice refresher of quadratics, but also some of this transformation application stuff. So it's a good recap with some little twists. So today I want to remind you how to find how to graph something like this by finding the vertex, intercepts, and find an x given a y and a y given an x. Also how to take something like this as the parent function and translate it using the completing the square method. Cool. Let's roll. What do baby parabolas eat? Quadratic formula. Finding the zeros. Zeros are when the y is 0. So this is like something for x but 0 for y. This is something for x but 0 for y. So one of the spots of interest we're interested in is the x's, and we call them zeros or roots or solutions or x-intercepts. They're all the same thing. Why can't they pick one? I don't know. But for that, I know that the y value is always 0, so we throw the 0 in for the y, and we factor or quadratic formula or complete the square, whatever you want to do to find those zeros. You guys are good at that. To find the y-intercept, this point is the y-intercept. That's 0 for the y, 0 for the x. It's not over that way, it's not over that way, it's right in the middle, which is 0. And something for y, I don't know what the y is, but to find this point, we know that the x is 0, so toss in a 0 for that, and a 0 for that. Most often, looks like a guy that's crying, maybe it should be upside down. Most often these cancel out, and you're just left with the c value, and often that's the y-intercept, just like y equals mx plus c. And this is the y-intercept, like if you had y equals 2x minus 3, that is where it starts, and this is how it dances. Rises 2, runs 1, there's your other point. This is the same thing. This is where it starts at 0, and this is how it dances, which is a little more complicated. But finding the y-intercept, throw in an x for 0 and solve. Moving through these quick because I think you know how to do it. I see you have some graph paper. You must be plotting something. Plotting, graphing, get it? Finding the vertex. The vertex occurs, there's one way to think about this. The vertex occurs halfway between the 2 points. So for example, if this was at 3 and this was at -1, halfway between those 2 points is 1, right? There's 4 units apart. You divide by 2, you get 2. You say -1 plus 2, or you'd say 3 minus 2, and you'd get 1. And that's the x value of this vertex. So it's 1 comma, I don't know, some y value. How would you find the y value? Let's call it a y value. Put the x in there and x in there, and then solve for y, right? So you get -1 plus 2, so 1, so 3, just like we kind of think, right? So that's one way to find it. You could find the zeros either by factoring or quadratic formula. There's another way to do it, which is this is negative b over 2a. It's the axis of symmetry, which I think you know and love, or maybe just know. And it comes from this formula broken up into 2 fractions, that fraction and that fraction. And if you interpret the results, it sort of says, if you want to find the 2 x values, this point and this point, start in the middle and go one way a certain amount. Let's do it in green. Go in a positive direction a certain amount, and you'll run into an x value. And go in the other direction a certain amount, and you run into the other x value. But this is the middle, and the middle is where the vertex is. And so we can also use the axis of symmetry, x equals negative b over 2a, to find the x value, and then take that x value, plug it in there, and get the y value out. Neat. I think you've done that before. Just moving through that. I always forget what these say. Find the vertex of a quadratic function by completing the square? Ain't nobody got time for that. We're going to do this completing the square later. So give it a shot. Make sure you can do it. Pause me and see if you can find the zeros, the y-intercept, and the vertex. Plot them. See what it looks like. Go. Pause me. Okay. So hopefully you said zeros occur when the y is 0. So you'd throw in, you'd set this equal to 0, and you'd solve for x, factoring or whatever. I would multiply everything by -1 to get rid of all those negative. It changes all the signs. This is 8, and then I'd probably factor it. So x and 4 and 2. The 4's got to be the positive one, and the 2's got to be the 2's got to be the negative one. So you get x is not equals. Just so therefore x equals 2 or x equals -4. So you'd plot those points. -4, 2. Great. The y-intercept occurs when x's are 0. Let's do it in red. On this line, all the x's are zeros. So you'd put a 0 in for that and a 0 in for that. They cancel each other out. Or I mean, they're 0. And so you're left with 8. So 8 is the y-intercept. It's not the top. It's not the vertex. The vertex is between these two. If I don't want to add them up and divide by 2, I'm going to use the axis of symmetry as -b over 2a. Just be careful with your signs. Negative b is -2, so it's +2, over 2a. A is -1, so -1. So this is at 2 divided. Oh, right. This is at 2 divided by -2, so the axis of symmetry is at -1, which means right in here. Nice straight line, Gorkevich. Then you want to find the actual y value for that. You take -1 as the x value, and you throw it in there and there. And you'd get -1 squared is +1, times -1 is -1, minus 2 times -1 is -2. Careful with your signs, plus 8. This seems like a straightforward thing, but like you guys are good at the algebra, but not at the negative signs, so be careful. So this is, I'm all over the place. -1 plus 2 plus 8, so 10 minus 1, 9. Sorry, that should look more like that. So 9, +9, which looks like it makes sense, and then draw it with a nice smooth curve. Sorry, drawing with a mouse. Smooth curve. Voila! Quadratic. And so it should look like that. Ba-bam! Great. Okay, so this is sort of a synopsis of finding the important points. If you want to re-emit that, however if you haven't jotted it in your notes, try that. If that helps. Okay, the other way, like once in a while, this way, finding all these points to sketch it is inefficient because you have to find like 1, 2, 3, 4 points. Sometimes it's nice just to see it as a transformation. So usually like this equation, it doesn't have an a term, so it's essentially just x squared. If you graphed it, it's moved over here. Zip. Ew. So we have to complete the square. Ow. And looking at this form of the equation, I can't see where it is. I can't see the transformation. But if you complete the square, which is this process that I'll walk you through a couple of times, this form, this is called standard form of a quadratic, turns into vertex form of a quadratic. It's called vertex form because the vertex is here at 2, -3. There's the 2. There's the -3, right? This is negative because it transfers. Which way? This way. Transfer my screen and your screen look a little different. But this is vertex form because it shows you the vertex, which is nice. And so it's easier if they gave the equation to you in this format. You know it's a y equals x squared. There's no a term in front. There's no a term in front. It's just a y equals x squared that's been moved around. And now that you know transformations, it's much easier to graph. You say, oh, it looks like this, but moved over and down. Voila. So let's try that out. Let's try to remember completing the square. Well, I think I remember something. Completing the square looks like this. These are all perfect square trinomials because if you factor them, they turn into x plus 5, x plus 5. You can call it x plus 5 squared, x minus 4 squared, x plus 6 squared. What's neat about these is there's a connection between these three components. If you're trying to turn this into a perfect squared setup, which I want because I want it to look like this previous slide, I want it to look like this sort of thing. I want to add right to the x. It'll help it move over. You'll notice that this value, 10, if you cut it in half, you get 5. And if you square it, you get 25. And if you take this -8, you cut it in half, you get -4. And if you square it, you get 16. If you take this trinomial and you cut it in half, you get 6. And if you square it, you get 36. There's this pattern happening that this value is always the b value cut in half and then squared. Right? So we said, oh, 10 cut in half divided by 2, 5. Square it happens to be this term. Same thing here. Cut it in half, -4. Square it, you get 16, right? And what we want to be able to do with that thing is say, if we have something like if we had like x plus 6x and nothing else there, or plus something, right? Plus something. What would I really want the plus something to be so I could make this different equation? So I could make this turn into blah 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 squared. Well, I'd take this, I'd cut it in half, 3, I'd square it, and that should be 9. And when you factor this, it turns into x plus 3 and x plus 3. Like this, we did that, so this is factorable. Perfect. This is essentially what we're doing here. Here's an x squared, an x and an x if you want to look at it visually. And here's 6 x's, which is really 3 by x. This is a 3 by x, and I have 2 of them, 3 by x. Right? And if you laid these out, this is x and this is x, so they sit next to each other nicely. Same with this, x and x. It's all sitting there nicely except for this piece, and that's what they mean by completing the square. How big is this piece? Well, it's 3 by 3. Right? So I need a square that's I need to add a square that's 3 by 3 to make this work out. Yeah, what is all this? Oh, I want this to be x by x. This is x squared plus 6 x's. Nice rectangle, Gorkevich. Plus 9. And why we want to do that is then because we can call this x plus 3, right? X plus 3 squared times itself. Right, so that's a visual way to look at it. If that's a little fussy, we can try these together. So what would we add to the end to make these a perfect square? Well, I'd cut this in half, 4, and I'd square it, so 16. That makes a nice perfect square. This thing factors into x plus 4 squared. Yeah. This you'd cut in half, 6, square it, 36, and this factors into x plus 6 squared. This you cut in half, -5/2, and you square it. And so you'd have to add, because you're squaring double negatives, you'd have to add 25/4 to that. And when you factored it, it would turn into x minus 5/2 squared, right? It's always this number that's in this factor, this number that's in here, this number that's in here. If you're not completely sure about that, expand it. X minus 5/2 times itself. This gives you x squared, ka-ching. This gives you positive 5 times 5 is 25, and 2 times 2 is 4. And when you multiply this times the x, you get -5/2 x and minus another one. So minus 5/2 x. This is 5 halves minus 5 halves is negative 10 halves x, and negative 10 halves is negative 5x, which is that middle term that we wanted. Yeah, don't be scared of fractions. Okay, if that's a little bit of a blur, that's okay. Let's give it a shot and try to solve this by completing the square. If we started this as it is, and I want to solve this, I want to turn this into a quadratic that is in vertex form. Maybe we started off. Maybe it started off life like this: plus 15 equals 0, right? And we switched this around. I kicked the 15 to the other side because I want to complete the square on this side. And so I want to turn this into x squared plus 16x. I want to complete the square. There's negative 15 still sitting over here. This we want to cut in half, so 8, and then we want to square it. So maybe I should do this with. There we go. It'll be cleaner than and a lot less clicking. So we want to add some value to this side to make this side perfect square, and we want to add the same value to the other side so it's balanced. We haven't done anything. So we're going to take the 16 and cut it in half, divide by 2. That's 8. Square it, you get 64. But we can't just add it to one side and not the other, so we got to add it to this side. Bing! And when you do that, that's really great. We did all that work, so this side becomes 49. This side factors into x plus 8 squared plus 49. And then you can, what's nice about this is you can take the square root, and the square root of 49 is something nice. You can solve things a little bit nicer by completing the square. That's one of the reasons that we complete the square. Another reason that we can complete the square is so we can turn it from one form to the other by completing the square. So if we want to take this and we want to turn it into this form, this vertex form, we're going to complete the square because it helps us just take x squared and move it over and down on the graph. So let's try it out. This looks like y equals x squared plus 4x. This 3, in this previous problem, we kicked them over to the other side. We're trying to essentially solve it for 0. Well, we kicked them over to the other side. Here, we can just sort of like push them out of the way and ignore them for a little bit and only really look at this piece. So with this, I wish there was something here. So in the next step, I could factor this into blah, blah, blah squared, right? And this component, the b term, we can cut in half, 2, and then square it, 4. And if we do that, what's nice about that is we can factor this entire thing into x plus 2 squared. And 3's still hanging out here, like, hey guys, wait for me. The only issue is we just gratuitously added 2 to the equation. Or sorry. We just gratuitously added 4 to the equation. And you can't do that. So in the previous problem, we added 4 to the other side, but there is no other side. It's just a y right now. And I want to keep it a y. So instead of adding 4 to balance it out, let's subtract 4, but let's do it outside of the equation. What's nice about that is that turns into x plus 2 squared, and that turns into negative 1. And so this is the exact same parabola as this, just in a different format. Now, this one's useful because you can use Pythagorean, quadratic formula and use A, B, and C. What's functional about this is it's easy to graph. I know that it looks like a quadratic. The quadratic is a parabola. Parabola goes 1 over, 1 up, 2 over, 2 squared is 4 up, 3 over, 3 squared is 9 up. So it's going to look like this on both sides. That's what my parabola looks like. But it's shifted 2 units left and 1 unit down. So 2 units left and 1 unit down. So its vertex is over there. Zip, zip, graphed, no problem. right? If you weren't sure exactly what it looks like, you know the vertex, so you put the vertex in and you say, oh, just like we did, this was the vertex and we said 1 unit over, 1 unit up, 2 units over, 4 units up, 3 units over, 9 units up. You can do that same thing from that vertex. So 1 unit over, 1 unit up, 2 units over, 1, 2, 3, 4 units up, right? And so it looks like that. Cool? If you graphed it, it would probably look like that. So the problem comes in when you have not a 1 for an A term. But that's okay, we can ignore our problems by factoring out the 3. And if you factor the 3 out, you're left with this trinomial inside. Divide by 3, divide by 3. Great. If we distributed that back in, we'd get the original. What's nice about that is that you can complete the square with that now by pushing that 1/3 kind of to the end of our thought process. Make them go hang out over here. Still in the parentheses. You could take half of this, and -4/3 divided by 2 is like saying times a half. And if you're multiplying fractions, you multiply everything on top, everything on bottom, and then you simplify, right? And that's your mathematical flexing, or your mathematical fraction skills flexing there again. So this is -2/3, right? And we want that to happen here, and we'll turn this into a, did we square it? I didn't square it. Gotta square it. Why didn't you tell me to square it? Squared. So this turns into +4/9. L. +4/9. Great. And that's in here. That's just in like this chunk inside. Here's the +1/3 over here. And because we added 4/9, you can subtract 4/9 on the outside. And all will be well with the world. And when you simplify that a little bit, this is still here. This inside turns into x squared minus, we said this was 2/3 when we did, oh, so not the squared, just x. Minus 2/3 squared. This is, in ninths, it's 3/9, so 3/9 minus 4/9 is minus 1/9. That's really good, but I don't want these big stupid parentheses. So we can redistribute the 3 into in front of that, because this is this chunk plus this chunk. So distribute it into here, and you get 3 times your x minus 2/3 squared. And 3 times 1/9 is 3/9, which is 1/3. So now it's sitting in vertex form, even with the A term. And what we can do with that is take the regular y equals 3x, y equals 3x squared, and say, okay, 0, 0, 1, 1 squared is 1, times 3 is 3, 1, 2, 3. 2 squared is 4, 4 times 3 is 12, so you do that right. You take that parabola and shift it like this. You'd shift it right 2/3 of a unit and down 1/3 of a unit to there. And so it would look something like that. Cool? Now, that's worst case scenario, and even if you could just follow me through that, that's great. Most of the things that you'll see are like this one. Try those techniques out in your home learning. There's this parabolas and completing the square. You can also try this one if you're not comfortable with completing the square yet. It's a good way to solve a quadratic. It's a little slow, but I like it mostly for finding the transformations. Cool. So you can either pause me or like just jump in your homework, or if you want to see one more, here's one more. If you're trying to solve this, or let's try to graph this. Let's call it y equals that. Forget about this piece and see what it looks like in vertex form. I would sequester this part of the equation, make 9 go hang out by itself, see what your C term is. So it'd be 10 divided by 2 is 5, 5 squared is 25. So I added 25 in here, so I should subtract 25 outside. We did all that work, so this turns into x plus 5 squared, and what this is, negative 16 outside. And so these are equivalent expressions or equations, but this one's nice because it takes y squared, which looks like that, and moves it 5 units to the left, 1, 2, 3, 4, 5, and 16 units down. Zip, zip. Yeah, easy to graph. 9, 1, oh. If you got negative 9 and negative 1 if you solve this for 0. Cool. Okay. Hope that helps. I'll see you soon. Bye. 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 Bye.